speaker, who is Alejandro Mus from the University of Valencia. And Alejandro will talk about the search for Galactic Center transients.
Yes.
In 230 GHz ALMA observations. So Alejandro, please.
Yes. Thank you, Sebastian, for the presentation, and thanks to the LOC and SOC for making this possible. Hello, everyone, and as Sebastian said, I will present you a first search of transients in the Galactic Center from 230 GHz ALMA observation during the 2017 GHz campaign. So this is a very recent submitted paper, and I want to show you my results. So, well, first I will introduce you to the Galactic Center and the motivations. Why is interesting in the Galactic Center, and why we are looking for transients there. Then I will talk you very briefly about the observations and the data analysis, and finally the results and the conclusions. So, as probably all of you know, the Galactic Center presents one of the highest stellar density in our galaxy. A lot of super interesting astrophysics is there. You can find supernovae remnant, you can find non-thermal filaments, a lot of things. So this makes its surrounding an environment potentially rich in radio transients. There are pulsars, there is one magnetar, and a lot of different kinds of flaring activity. So we have done the first study of transitivity in the Galactic Center during the 2017 GHz campaign. So the idea was, if we can find a transient, can we reconstruct a movie to see the transient appearing and disappearing? Well, first, let's talk about the source. Seen by ALMA, the Galactic Center can be decomposed in two parts, an extended part called mini spirals, where you can find a lot of molecular clouds, super interesting things, and there is where we want to find transients. And a compact source, a supermassive black hole, which is the center of our galaxy, called Sagittarius A star. This is a supermassive black hole, but not that massive in comparison with, for example, MAYA2022. In particular, its ISCO have periods of only 4 to 30 minutes. So this quick and this very rapid variation and the dominance of this source on the image makes very difficult the transient search there. So how we can deal with those two problems? We had to develop a new self-calibration method. Let's talk about the observations before entering details. So ALMA was and is a key station participating in the GHz. Without ALMA, MAYA2022 would look like is right now, or without ALMA, there would have been polarimetry in MAYA2022. The VLBI observations of ALMA were part of the cycle 4 campaign, and they were in compact configuration. The campaign were divided in two parts, but we are only focused here in the 230 GHz. So for the Galactic Center, April 5, April 6, and April 11. In particular, April 5, where the Galactic Center was observed during 6 hours, April 6, 10 hours, and April 11, 5 hours. And why I want to highlight this? Because never before the Galactic Center was observed that long by ALMA. Actually, ALMA didn't recommend us. I'm part of the GHz, so that's why I talk of we didn't recommend us to observe for that long, because the Galactic Center has very low elevations. So we had to push ALMA to its limits. And you will see at the low elevations how this is very hard to deal with. There were a medium number of 37 antennas of 12-meter diameters. ALMA is such a good instrument that we were not limited by noise, but we were limited by calibration. So ALMA is very important in the GHz. And a question that I want to solve here is why we had to strain ALMA to its limits? Why it was so important? Because we want to make very long baselines, right? So we want to join, for example, ALMA in Atacama with Pico Veleta in Spain. So yeah, that was a very huge, a very important experiment, never did it before. Let's go for the calibration. So we defined the visibility model in the following way. We first take an standard, the normalized standard flux, which I highlight here with a circle, more or less I did by hand. And we take the flux of the black hole here. What we want to do is first that this new algorithm could model Sagittarius A star and flag it because it's dominating the image. And then second, using the mini spirals, which are constant because they are very huge. They take 30 arcseconds of the FOV, so they can be considered constant in time and use them for calibrating and removing the fast variability. Moreover, since self-calibration, when you are self-calibrating, you are losing the absolute position, we had to take care of the astrometry. So we include here some parameters of the offsets in relative extension and relative declination. So we were actually taking into account almost everything. Let's go for the astrometry. In this example, I took one particular epoch, and in crosses or blue, there is the declination offset, and in pluses or green, the right extension offset. In continuous line or red is the antenna elevations. So we can see how the offsets, while antenna elevations are high enough, are almost zero. They can be considered zero. However, when they start to be lower, since ALMA, so the atmosphere between ALMA and the galactic center is starting to increase, this offset starts to increase exponentially as well. So we have to take care of this astrometry during the self-calibration for the suboptimal elevations. Now let's go for the flux part. So as probably all of you know, we can model fit the observed visibilities with the model visibilities by minimizing the chi-square. But still, how do we deal with the problems? So the dominating source, Sagittarius A star, and the fast variability. So we consider this gain, this number. What we're saying here is basically the flux has to be constant. We scale it by its mean, it has to be constant, which we know it because the standard source is constant. With this, we can produce a correct estimate of the Sagittarius A flux density. And now that we have the model strategy, we can go through the search for transient. So first of all, we need to define threshold, critical threshold. And we consider critical threshold in time and RMS. So excursions such that they survive up to 3 times the correlation time, so up to 12 seconds. And they had an RMS of at least 7 times the instantaneous RMS between consecutive images. They were potentially transients, but not transients, because then we had to manually inspect all of these elements. Even we manually inspect the elements which were not satisfying one of these 2 conditions, just to be really sure, just to be the maximum conservative that we could be, to check if they were potential transients or they were bad data. We manual image each snapshot for creating the movie, but by using this gain during the self-calibration to update our observed visibilities. Then when we had this clear, we went to synthetic data. We took 1 day, we remove all the real data that was there, and we include a compact central source, an extended source, and a short transient, a little bit offset. So we had control on this data, and we want to verify if the this novel self-calibration and this strategy for finding transients was working. Thermal noise and antenna gains were equal to the real observation. So we imitate the real observation. In this example, in the left panel, you see the dynamic range versus the UT. And in red, or continued line, again, the antenna elevations. Around 11, we see a peak and excursion, and because of time limitations, I don't show you more statistics, but if we go and we check both conditions, so we do integration time of 12 seconds, this peak is still continuous. In the RMS setting, again, we see around 11 a peak. So we manually inspected and we didn't move it. You see here how this transient disappeared. So we have the residual mass and suddenly pop, a point is here. So it seems everything is working fine. Let's go for the real data. Again, for the real data, we did the same statistics. In each row, you find here April 5, April 6, and April 11 observations. And in column, the dynamic range for seconds iteration time, the RMS 4 seconds iteration time, a zoom in critical areas, so at the beginning and the end of the scans, or places where we thought there could be transients, and then a time average to 12 seconds. We can say that we didn't find any transient, unfortunately. However, you see some points here and you say, oh, what this could be. So to be really sure that those were not transients, even if they didn't survive to the time averaging, we manually inspected. And we took this point, for example, and I showed you movie.
We have 3 minutes.
Okay, perfect. So I will leave the movie. We don't see anything. And this point is a byte data due to antenna problems. Or calibration, because the method is very good, but it's not perfect, right? So, and with this, I'm finishing. We did the first transient search at high frequencies using ALMA. And this, in the Galactic Center, needs or requires special treatment because it's dominated by the central black hole and is fast varying. We present a novel non-standard self-calibration procedure to solve these two problems. For this, we only require two things. One, to know the source structure and to detect the whole flux. So it could be applied to any source that can be decomposed in these two, or that can satisfy these two hypotheses. So there is a one compact and a stable source, and the one compact and fast varying source, and one extended and stable source. And the relative flux between them is great. This strategy allows us to estimate antenna gains, and with this, to get a more precise information of the light curves of the compact component, so of Sagittarius system. No transients were found, but this new self-calibration applied to future ALMA observations will improve astrometric and variability analysis of the Galactic Center and will increase the probability of finding transients in this region. And with this, I finish.
Thank you very much, Alejandro. Listening to you, it seems very easy to calibrate those data, but we know that the devil is in the details, right?
Yeah, exactly.
I have a quick question on the data. Did you try to see the polarization? And you see do you see some variation in the polarization signals?
I can't answer you this. We are doing that, but I can give you more details.
So we can take more questions from the chat then.
Yes, certainly. There is already a question. Very impressive work and very detailed. Thanks for the talk. Regarding the inclusion of the different components in the self-calibration process, can you repeat again, how do you create the model of the extended component? Do you use all the data of one single day to create it, or just small integration time ranges?
Yes.
How? yeah, so there's further question, how can the different UV samplings affect the generation of the model of this extended component?
Okay, yes, thank you for the question. So this can be quite detailed. April 5 and April 6 presented a very good weather and very good UV coverage. So we have created the model for each day separately. April 11 was a little bit worse, so it was harder to analyze. We can see it in these plots here. So you see it's more dispersed. And for every day, we took the whole data and we filter the data coming. So by some tricks of taking the long baseline and short baselines, we filter the compact component and the extended component. And we compute the flux of the compact component, we compute the flux of the extended component, and we create this model. So we could split, we could get this part and this part. I hope I could answer the question.
Yes, I think that was great. Thanks. There's also another question. Can the transient search be done for other targets? So for not Galactic Center, but to the other targets of the EHT program?
Well, in the EHT, we are focusing on the Galactic Center and MAYA2022. There are a lot of people looking for pulsars in the Galactic Center because the region is potentially rich for this kind of activities. But in MAYA2022, as far as I know, in that region there is no so many chances of finding transients. So if you have to bet, if it's very hard to find transient and pulsars, and if you had to bet and do an observations and apply for an observations, I would do it in the Galactic Center, not in another place, unless you are really sure that you can find one there.
And just as a follow-up to that, what kind of events can be seen as transients? So for example, tidal disruption events, would they turn out as transients or would they look differently in your analysis?
So any event, for example, X-ray burst, flares activities, any event that can survive up to 12 seconds can be seen there. Even a rotating star, but pulsars, they have very short transient activity. But if they were long enough, they could be seen there as well.
Excellent, thank you so much.
Maybe I can ask one more question. We still have a few more time. Not too tight, you can answer more. I have a question about the astrometry and the correlation with the elevation. So this is just due to the atmosphere, right? Is atmospheric dispersion?
Yes. Or? In principle, yes, this is due to the atmosphere. We haven't entered in the full details, but we have considered along the work that this is due to the atmosphere because even in the real data, we see the same correlation. So at the end, in the bad days, mostly in the bad day, right? So here and here also.
Is this something that can be modeled and put as a model in the antennas? I mean, in the software at ALMA, or does it depend on the weather conditions? Or
I can give you an answer, but sorry, I can give you. I think it depends on the weather conditions. I have to revise how was the weather condition during the observations. I have it somewhere in my computer, okay, but I can give you an answer now.
And what is the elevation where it become critical?
So up to 40 degrees, more or less, the mean was 40 degrees when it's becoming critical. Yeah. Okay. And then so we flag 25 down, we flag everything.
But this is because you are observing at very low elevation.
Yeah.
This is not the normal mode for.
This is the normal. Yeah.
Okay. Well, thank you again. Alejandro, it was a fantastic talk.